And this is independence in the multiplication rule. And for some definitions, two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. Okay, example that. I'm pulling two cards out. I'm looking at getting the probability of two kings. Okay, if the person pulls a card out at random, and so forth, the probability they're going to get a king is 4 out of 52. Now, they put the card back in. Then the second time when I pull a king out, it's basically the same probability because we still have the 52 cards. Now, compare that against, that's independent. Compare that against if I take a card out and it's a king, and I take that and I set that card aside. Now instead of there being 52 cards, now there's 51 cards. So those are dependent. That's what they're talking about there. Now if you get independent events, and you got the probability of E and F, then it's equal to the probability of E times the probability of F. Now sometimes the and is implied. If I say what's the probability you're going to get 3 cards and all of them are kings. Well, what's implied there is the first card is king, and the second card is a king, and the third card is a king. So you may not actually see the word and in there. It's implied. What's the probability you'll get 3 of a kind? Well, that's, again, an and there. So, and it says can have more than 2 events. So you can have however many. Well, let's take a look at this first one. Probability of E is equal to 0.5. Probability of F is equal to 0.3. And it says E and F are independent. What's the probability of E and F? Well, from the formula we just looked at, probability of E and F is equal to the probability of E times the probability of F. So we're going to have 0.5 times 0.3, which gives us 0.15. Now, what this notation indicates, we've talked about a little bit. And again, here's A and B, but you can have any letters there. Probability of A and B equals probability event A occurs in the first trial and event B occurs in the second trial. Let's take a look at finding a probability. It says what is probably rolling a die and getting a 5, and flipping a coin and getting heads. So 5 on a die and heads on a coin. Well, me rolling a die has nothing to do with flipping the coin. So these are independent. Now we look at the probability of getting a 5 on a die. There are 6 faces on a die, and one of them is a 5. So that'd be 1 6. Now for heads on a coin, well, there's 2 possibilities, heads and tails, and of those, one of them is a heads. So we get 1 6 times 1/2, which gives us 1/12. And put those into decimal form, put them into fraction form, whatever's appropriate. When I say whatever's appropriate, the book, if they have it in decimal, you can put it in decimal to check your answer. Comes test time, what I'm looking for is a setup, because I want to make sure you know how to set it up. Sometimes you can work a problem wrong, and then you look at the decimal, and with rounding, maybe you still come out correct. And again, I'm interested in whether you understand the setup. Okay, our third one. Given the probability you're going to die from cancer versus other causes is 0.23. And I actually looked this up on I think it was CDC's website. And it is 23%. What is the probability that 4 people picked at random are going to die from cancer? You'd be surprised. The one that's largest is heart disease. And statistics are funny, and I like to mention this because my mother passed away last December, and she went to bed. She'd been sick, had a flu or a cold or something, and when they went in the next day, she had passed away during the night. Well, they didn't do an autopsy, and they're not quite sure, what happened when I asked them. When I got the death certificate back, the cause on there was heart disease. I was told that, or not told that. I saw it on a show one time that if they don't know what caused the person's passing away, they just put down heart disease. So it's kind of deceiving when you see up there and it has heart disease so high. Granted, no matter what happened, it caused her heart to stop. That doesn't necessarily mean heart disease. But anyway, I go off on a tangent on how people abuse statistics. Okay, what is probably if 4 people picked around going to die from cancer? So 4 people die from cancer. Now what this means is the first person dies from cancer, and the second person dies from cancer, and the third person dies from cancer, and the fourth person dies from cancer. So there's implied ands in here. So it's multiplication. Well, the probability that one person is going to die from cancer is 0.23. So we're going to take 0.23 times itself 4 times, because we've got 4 people. Now another way of writing that is 0.23 to the 4th power. Now to show that in the calculator, if you're not very familiar with exponents, no matter what, if you're in something you're not sure what it is, just do a second mode that gets you out. Okay, we do 0.23, and you do caret and then 4, and enter. And that gives you your probability. So 0.0028 would be our probability. Let's look at our next problem. It says we're rolling a pair of dice. What is probably we get a total of 7, counting the dots 4 times in a row? Well, let's talk about dice first. This is the problem. Problem is that. Oh, I skipped one. Sorry. Okay, problem 4. Given a standard deck of cards, and we pick 3 cards out with replacement. That means we pull out a card, we look at it, and then we put it back in. What is probably getting 3 kings? Well, that means the first card's a king, and the second card is a king, and the third card is a king. So the and's there, it's multiplication. These are independent because I'm putting a card back in the deck. So first time through, there's 52 cards, and there's 4 kings. So the probability I'm going to get a king is this. Okay, so I envision this. I got a king of hearts. I pull it out, I look at it, that's nice, and I put it back in the deck. So there's 52 cards again, and 4 of them are kings. Pull out another king, look at it, think that's nice, put it back in. So I got 52 again, and 4 on top. And where's my calculator? There it is. 4 divided by 52, caret 3. That's interesting. When I plugged in my calculator, I couldn't have asked for a better time to show this. I get this right here, and I'll round it to 4 decimal places. What this is scientific notation. What this means is e to the negative 4 means move your decimal point 4 places to the left. So our answer is actually 0.00045517. And if I were to round it to 4 decimal places, that'd be 0.0 3 zeros and then a 5. Let me save this. What is this called? Independence and the multiplication rule. application rule. Page 01.pdf. There we go. Now let's look at problem number 5. Okay, we're rolling a pair of dice. What's probably we get a total of 7. Total of 7, 4 times in a row. So first time will be a 7, second time's a 7, third time's a 7, and the fourth time's 7. So there's an implied and there, isn't there? Okay, let's talk about the different possibilities. You could have first die has a 1, second has a 1. First one has a 1, second one has a 2, 1 3, 1 4, 1 5, 1 6, 1 7. Then it could be 2 1, 2 2, 2 3, 2 4, 2 5, 2 7. I better go to bed. Okay, never mind that. These are not the droids you were looking for. Now, as I list the possibilities, I keep going here. What we're going to find is that there's a total of 36 possibilities. Now, specifically, see how we got 1 2 here, and then we got 2 1 here. Getting a 1 on the first die and a second on the second die, or a 2 on the first die and a 1 on the second die, those are 2 separate events. But the 1 1 only occurs once. So keep that in mind. Okay, so let's go back to here. We're looking at getting a total of 7, so a sum of 7. Think what could give you 7? Well, 1 and 6 would. 6 and 1 would. 2 and 5 would. 5 and 2 would. 3 and 4 would. And 4 and 3 would. Those are all the combinations that added together to give you 7. Now there's 36 total. And 1, 2, 3, 4, 5, 6 of these. So that's 1 6. Now here, that's for that's for your possibility on your first roll. We got 3 other rolls where we're going to get 7. So this will be 6 out of 36, 6 out of 36, and 6 out of 36. Now these are 1 6. So that'd be 1 6 to the 4th power, which would give us another scientific notation. 7.716049383 e to the negative 4. Again, we'll move our decimal place 4 places to the left, and we get 30 7716049383. And rounded at 4 decimal places, we get 3 zeros, and then an 8. And that would be our possibility. Now, the next one talks about the least 1 probabilities. This is of the form when you got a problem that says find probability of at least 1 something out of n. And it could be anything there for the something. First step is write as 1 minus probability of none something. Then write as 1 minus probability of all opposite of something. And 3, write as 1 minus probability of all and then opposite of something to a power. So let's look at this. I'm going to do this example. Out of 5 births, find a probability of at least 1 girl. So at least 1 girl out of 5 births. Okay, let's go back up here to our form. First says to write this as 1 minus probability of none or no, and then whatever we're talking about. The something, at least 1 girl, this will be our something, the girl. So none girl, no girls. Maybe that'd be better to math or English-wise to say that. Remember I said none or no. So 1 minus probability of no girls. Well, then we rewrite it as 1 minus probability of all. So the no or none changes to all. And then we go the opposite of girls. See, we got something here, and this is opposite of something. So opposite of girls is boys. And then down here we're going to put the power on there. When we say a probability of a boy, we look at one child, and the probability you get a boy is 1/2. And now we're talking out of 5 births, so that's what determines what our exponent is, how many we're talking about. And if I were to put this in my calculator, 1 minus 1 divided by 2, carry it to the 5, we get 0.9688, rounding to 4 decimal places. So if you're going to have 5 children, the probability you get at least 1 girl is pretty good. Let's look at our 6th example here. Test contains 25 multiple choice problems. So 25 multiple choice, each with four parts. So I got 4 parts, like an A, B, C, and D. Only one of which is right. One of which is right. Means the other 3 are wrong. You're guessing. What is the probability you get at least 1 right? Okay. So at least 1 right. And you're guessing on every problem. And let me put that here. At least 1 right out of 25. Okay. Look at our steps here. We rewrite as 1 minus probability of none something, or no somethings. And in this particular problem, at least 1 right. This is our something. So at this point, it just carries straight down. So 1 minus probability of none right. Now then we change it to all, and we change the something to the opposite of something. So this is going to be 1 minus probability of all, and the opposite of right is wrong. Now you want to keep this really simple. Even if you got it really wordy up here and at least 1, try to choose a 1-word description that sums it up. Because then when you flip it to the opposite, it's a lot easier to flip. Even if you're technically a little bit off, just as long as you can get it to 1 word. Okay. Let's look at the probability for one question that you're going to get it wrong. Well, if there's 4 parts and one of them is right, then the probability you're going to get it wrong is 3 out of 4. Now there's 25 questions, so that's going to be our exponent. So we'll have that, which gives us 1 minus 3 divided by 4 caret 25. And rounding to 4 decimal places, I got 0.9992. And that'd be our answer. Let me save that, and let's look at our last problem. Okay, number 7. The odds you will die from fireworks is 1 in 652,046. They compile all this, so you're going to die from fireworks is 1 out of 652. I don't remember where I got this one at. Some kind of government website. That. It says, what is the probability that out of 5 people picked at random, at least 1 will die from fireworks? So we're looking at probability at least 1 will die. Out of, how many are we looking at? 5 people. Well, first thing we do is we write it as 1 minus probability of none somethings. And our something will be the die. So 1 minus probability of none die. Well, next part we change none to all. And we change die to the opposite of it. So all live. Okay, let's talk about probability somebody's going to live. If they're going to die from fireworks is that, then the live will be 1 minus that. That's the complement rule. Now you can put that, actually put that inside the parentheses if you want, but we'll go ahead and simplify it. That'll give us 652,045 over 652,046. If one of them is going to die out of that many, then this many will live. So we'll have 652,045 over 652,046. And out of 5, so the how many goes as your exponent. So let's see what we come up with. So 1 minus 652,045 divided by 652,046 caret 5. And we get 7.66814713 e to the negative 6. This is the problem with rounding to 4 decimal places. This e to the negative 6 means I move my decimal 6 places to the left. So I'd have 1, 2, 3, 4, 5, 7, 6, 6, 8, 1, 4, 7, 1, 3. If I were to round this to 4 decimal places, it'd be 0. Probability would be 0. I'm going to take it out more. I'll take it out to 4 significant digits. So I'll take it out that far. I don't like how some books will automatically just round to 4 decimal places. It's better to go with significant digits. Instead of with significant digits, you ignore those leading zeros. And I think that's the last problem. Yes, it is. Save it. And stop the recorders. This is on conditional probability and general multiplication rule. Now, conditional probability, the notation probability, and then you got inside of parentheses, F, and then that vertical bar is given. So, probability of F given E is red. Probability of event F given event E is probability of event F occurs given that event E has occurred. Now, you shouldn't get thinking that it's always E and F. It could be A and B. It can be anything. Excuse me. Now this is where we're narrowing it down. We're only looking at a subset. For example, maybe I'm going to find a probability of picking somebody at random from the class who's wearing glasses given they're female. So I'm only looking at women, and then from there figuring my probability. Now our conditional probability rule goes like this. Probability of F given E is equal to probability of E and F over the probability of E. Now you can also write it as, see this N here? That's the number of outcomes. So the number of outcomes in E and F over the number of outcomes in E. Take a look at this problem. Suppose the E and F are 2 events, and probability of E and F is 0.5. And probability of E is 0.7. What is the probability of F given E? Let's go back up to our formula. Okay, so from our formula, probability of F given E is equal to the probability of E and F over the probability of E. Probability of E and F is 0.5 over the probability of E, which is 0.7. And try and get over being sick. It's got 0.5 divided by 0.7. 4 decimal places, 0.7143. Yep, that's our answer. Take a look at this one. It says suppose the E and F are two events, and then the number of outcomes of E and F is equal to 300. The number of outcomes of E is equal to 800. What is the probability of F given E? So the number of outcomes of E and F is equal to, what did I say, 300? And number of outcomes in E is equal to 800. And they want to know what's the probability of F given E. Well, from our formula, it's number of outcomes of E and F over number of outcomes of E. See how this equals kind of goes like this? This is saying this is equal to this, or this is also equal to this. So you can match either one together. So we're going to have 300 over 800. Which gives us 0.375. And that's our answer. Okay, let's look at this problem. It says suppose that E and F are two events and probability of E is 0.7. And probability of F given E is equal to 0.3. Says what is probability of E and F? Now we're going back to our same formula here. So we're using this one we did in problem 1. We're just given different information. So we got probability of F given E is equal to probability of E and F over the probability of E. Well, the probability of F given E is 0.3. Probability of E and F we don't know. We treat it like a variable. And probability of E is 0.7. Well, if you remember from college algebra, solving this, we'd multiply both sides by 0.7 to get rid of the fraction. And 0.3 times 0.7 gives us 0.21. And I do apologize for my congestion and everything. Okay, let's take a look at our fourth problem here. Given the general population, 12% are old. In addition, 8% are old and forgetful. What is probably a random select person will be forgetful given they are old? So what they're asking for is probability that they will be forgetful given they are old. So forgetful, or can't spell. Forget, F-U-L, yeah. Given they are old. This is what they're asking for. Up above they said given general population 12% are old. So probability of old is 12%. In addition, 8% are old and forgetful. So old and forgetful. Are 8%. Okay. That's all the information they give us. Well, this is a variation of this problem we just did. So probability of F given E is equal to probability of E and F over probability of E. Well, F given E, that would indicate to me, here's my given, so this one is our F, and this would be E, which means this is E here, and this would be E, and forgetful is F. Now, you see how that matches up with our formula. So this is what they're asking for right here. So probability of forgetful given or old. And this is probability of E and F, which is probability of old and forgetful. So old and forgetful over probability of E, which is probability of old. Well, they give us old and forgetful, 0.08. And they give us old, which was 0.12. So 0.08 divided by 0.12. You get 0.66, 3 sixes and a 7. Excuse me. Somebody put me out of my misery. Okay, let's look at one more of those. It says for 18 to 20-year-olds, 27% believe in aliens and ghosts. Given that 35% of 18 to 20-year-olds believe in ghosts, given they believe in aliens. So probability of ghosts given they believe in aliens. I'm kind of shortening it there. But probably given 35% believe in ghosts given they believe in aliens. That's 35%. Now this is going to match up against our formula. Probability of F given E. So ghosts is going to be our F, and aliens will be our E. Okay, see what else they give us. 27% believe in aliens and ghosts. Aliens and ghosts. So probability of aliens and ghosts was 27%. And this is our E, and this is our F. Actually, I want to do this in red. Not that it matters. So that's E, and this is F. There we go. Which is probability of E and F. So this is 0.35, and this one is 0.27. And then it says, what probability of believing aliens? So they're wanting us to find probability of aliens. And aliens, we already said, was E. So they're wanting us to find a probability of E. Well, this goes back to our formula. So we got probability of F given E is equal to probability of E and F divided by probability of E. Well, let's put in what they give us. They gave us probability of F given E, which is 0.35. Probability of E and F is 0.27 over the probability of E. If you remember from college algebra, when we're solving an equation, we always get rid of the fraction first. So we'll multiply both sides by probability of E. So that would give us 0.35 probability of E is equal to 0.27. And then we'll divide both sides by 0.35, and we get probability of E is equal to 0.27 divided by 0.35. 0.27 divided by 0.35. And so the probability of E, which is the probability of aliens, is 0.7714. Let me save that. Conditional probability and general multiplication rule. Conditional and general multiplication rule. Page 01. There we go. Well, let's look at number 6. Tables are a little bit different when we're talking about probability. Some ways are easier. It says given the following table, we got hair color and then male and female and totals. So that means that for males, there's 25 brunettes, 5 blondes, so forth. Okay, A. What is the probability a random select person is female given they have red hair? So probability of female given red hair. And you want to keep this short. You don't want to get real wordy on this because words will throw you. Given they have red hair. So we're only looking at red hair. There's 9 total. Of those 9, 7 of them were female. So we have 7 ninths. I won't actually plug that in my calculator, but you could. Now B says, what is the probability that a randomly select person has blonde hair given they are male? So we're only looking at the males. So probability of blonde hair given the males. Okay, so how many males are there? There's 32 males. And of those 32, there's 5 of them have blonde hair. So we'll have 5 out of 32. Now our general multiplication rule looks like this, and it looks pretty complicated. It's actually a fairly simple idea. The formula makes it look hard. The formula comes in handy if we're given numbers. So if they're telling you these percentages, what probability of E is, and what probability of E and F is, and you're asked to find the probability of F given E. But for the most part, these are a lot easier to work than that. Probability of E and F is equal to probability of E times probability of F given E. So this first one happens, and it reduces the probability of the next one, or changes it in some way. Those are dependent events, is what that's referring to. Well, let's see some examples, see what in the world this is really saying. Okay, suppose the 3 cards are randomly selected from a standard deck of cards. What's probably getting 3 queens with replacement? With replacement, it means we take a card out, we look at it, we put it back in after we're done. Okay. So probability of 3 queens. Now the addition rule is kind of complicated. Or maybe I shouldn't say complicated. It isn't as easy to see as the OR. The OR, the multiplication, the OR is the addition. Well, you actually have the word OR there. But for multiplication, the AND is implied. This is saying we'll get a queen the first time, and the second time, and the third time. So I'll put Q for queen. So we're saying like queen and queen and queen. Well, AND is multiplication. So I'm going to have 3 fractions multiplied together. Now our first one, there's 52 cards, and we're looking at the probability of pulling out a queen. Well, it's 4 queens. So that'd be 4 out of 52. Let's say it's a queen of hearts. We look at it, so think that's okay, that's nice. We put it back into the deck. This is worth replacement. Yeah, worth replacement. So we put it back in the deck. Well, there's 52 cards again. Out of those, 4 of them are queens. Okay, we pull out another queen. Queen of diamonds. We look at it, think, okay, that's nice. We put it back in. There's 52 cards again, and of those, 4 of them are queens. So this will give us our probability. Caret 3. So this gives us 4.5517 e to the negative 4. Now what this notation means is scientific notation. That means like times 10 to the negative 4, which means we move our decimal place 4 places to the left. So this will be 4552. Excuse me. Let's look at B. B says, what is probably getting the three queens with no replacement? So we pull a card out, look at it, and we keep it out. We don't put it back in the deck. Okay, so we're looking at 3 queens again. And again, there's an implied AND. First card, 52 total, there's 4 of them are queens. I actually envision pulling a card out. I find it better to do it that way than do it in theory. Just think it strictly in theory. I pull the queen of diamonds out. I can draw a diamond, but I pull the queen of diamonds out. Well, how many cards are there left in the deck now? Well, there's 51. Of those 51, how many queens there are? Well, we pulled out 1, so there's 3 left. Now, this time I pulled out the queen of hearts, for example. Well, how many cards are in the deck? Well, there's 50 left, because we pulled 2 of them out already. They're already sitting here on the table. And how many queens are left? Well, there's 2, because we pulled 2 of these out. We pulled that queen of diamonds and queen of hearts. Now, this is a very specific example to demonstrate what are we talking about. But again, it helps you to visualize it. And 4 out of 52 times 3 out of 51 times 2 out of 50 1.80995 e to the negative 4. Again, that means I move my decimal place 4 places to the left. 1, 2, 3, 1, 8, and I'll just do there. That would be our probability. Excuse me. Okay, number 8. Says there are 10 men, 13 women. 2 are selected to attend a statistics conference. What is probably the 2 are selected at random that they are both women? So we're looking at woman and woman. Now it doesn't make any sense to take the same woman twice to the same conference. We want like two students to attend it to get to be represented. Well, there's 23 total, and we're looking probably the first one's a woman. Well, there's 13 of those 23 are women. Okay, now imagine June's in the class. We picked June. She's sitting out in the hallway now, waiting to go to the conference. How many students are left? Well, there's 22 now. And of those 22, 12 of them are women, because we already pulled June out, so she's no longer in the mix. So that's 13 over 23 times 12 over 22. And we get 0.3083. That'd be our probability. Number 9. Given a standard deck of cards, what is probably getting 3 of a kind? 3 2s, 3 queens, etc. An example hand: queen, 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 2, 5. We cannot have 4 queens since that would be 4 of a kind. Note, assuming you are dealt the first 5 cards and the first 3 are 3 of the same. Just to make it very simple so we don't think too hard on it. So probability of 3 of a kind. Dealt 5 cards. Like that. There's 52 cards to begin with. And 3 of a kind, like 3 2s, 3 queens. Well, the first card would be 52 out of 52. Because we didn't say it had to be like 3 queens. We said 3 of a kind. Now, this first one decides what we're working with. Let's say I pull out a king. Queen of hearts, or king of hearts, I mean. Well, this then says 3 of a kind. We need 3 2s, 3 queens. We need 3 kings. Okay. We pulled the king of hearts out. There was 51 cards left. Of those, we're now looking for kings, and there's 3 kings left, because I pulled the king of hearts out already. Okay, let's imagine this one is a king of diamonds. And, okay, so the next one, there's 50 cards left in. Of those, 2 of them are kings. And, king of clubs. I'm not going to try to draw a club because I'll open myself up to ridicule, but, let me shift my position here. There we go. This is a king of clubs. So again, these are just examples. I'm envisioning this. Okay, so I'm done. I got my 3 of a kind. My next card is 49 left. I can pick anything except for a king. Well, there's we pulled 3 kings out, so there's 1 king left inside. So I can pick from any of the other 48 cards. It just can't be a king. Let's imagine it was a queen. Queen of hearts. Okay, that means there's 48 cards left here. And there's 47 for me to pick from, because one of them is still a king. So I want anything except for that one. So let's see what that gives us. Three out of 51 times 2 out of 50 times 48 out of 49 times 47 out of 48. And we get 0.0023, rounding to 4 decimal places. Okay, let's look at our 10th example here. So in a box we have 10 black, 5 blue, 3 red, 7 green. Now A says, we are choosing 2 markers at random. What is probability they're both green? Now, we're choosing 2 markers, which means we're not putting them back in, so no replacement. And probability they're both green. So we're looking at probability of green, green. Well, how many are there total? There's, let's see, 8, 15, 25 total. And there's 7 green ones. So that'll be our first marker. Now, envision, we just pulled a green marker out, so it's sitting out there on the table. So there's 24 markers left. And of those, 6 of them are green. I won't actually plug these in our calculator, just do the setup on them. But I would recommend you plug them in to verify whether you got the answer right, looking in the back of the book. B, what is probably first is green and the second one is black? So probability of green and then black. Well, it's 25 total, 7 of them are green, times, there's only 24 left, and I want the second one to be black. Yeah, black. So that'd be 10 out of 24. C says, what is probably first is black and the second one is green? So probability of black, green. Well, this is 25. There's 10 black ones. I pull one marker away, so there's 24 left, and there's still 7 green ones, though, because I didn't put any green ones away. Okay. D. What is the probability? One is black and one is green. So one is black. And one is green. Well, that means I could have a probability of black and then green, or I could have a probability of green and then black. So, because it doesn't specify order, does it? Okay. Well, we actually calculated these up above. Probability of black, green is C. So that'd be 10 out of 25 times 7 out of 24. Or, in addition, is plus. And then we did this in B. Probability of green and then black. So it'd be 7 out of 25 times 10 out of 24. And those would be your answers. Now, we have a note here. It says if small random samples are taken from large populations without replacement, it is reasonable to assume independence of the events. As a rule of thumb, if the sample size is less than 5% of the population size, we treat the events as independent. What is that saying? Okay. Let's say there's 300,000 people in Wichita. There's a little bit more than that, but there's 300,000 people. And let's say 150,000 of them are women. I guess there's no kids in our Wichita. If I look at the probability of picking out 2 women, woman and woman. Well, there's 300,000 people on the bottom there, and 150,000 would be up on top. Now, normally what we do is we would subtract 1 from these. So this would be 299,999, and this would be 149,999. Like that. Well, let's go to our calculator. 150,000 divided by 300,000. gives us 0.5. 149,999 divided by 299,999 gives us 0.49999833333, so forth. Is there really that much difference between this one and this one? There isn't. So when you're talking about large numbers like that, instead of trying to reduce it like that, we just pretend that they're we assume independence of the events, which means that this second one is also 300,000 on the bottom and 150,000 on top. Again, from the fact that when you're dealing with large numbers like that, it just doesn't make any sense to try to reduce it by one, because it goes so far out there anyway, decimal places, that it's practically the same. Now the last thing, they say two events E and F are independent if probability of E given F is equal to E, probability of E, or equivalent. The probability of F given E is equal to probability of F. They'll give you some problems where they will ask you if E and F are independent. Well, all you do is find this probability here, find probability of E and F, or E given F, and then you find the probability of E. And if they're equal, then that means they're independent. So nothing real exciting there. And we're done with that section. So let me stop the recorders.